Bismillahirrahmanirrahim. Welcome to Network Analysis. This is episode 13 and let's start today's discussion before wasting any time. First of all, I just wanted to tell you that we are just in the previous discussion wrap up about the second topic, that is the inductive parameters. We finally developed a voltage and the current relationship in the previous episode. So we are now able to discuss a case of the example in today's discussion, like inductive parameters. Let's discuss an example case for the better understanding. So if you see here, this is a graph where in the horizontal axis time is drawn and the vertical axis any quantity that can be controlled is drawn. Usually time is taken always in the horizontal axis because it is the independent variable. We can't control it. It is always varying according to the nature. So usually current can be varied according to our situation. It is taken in the vertical axis. In a certain inductive system, any type of inductive system, current waveform shown in this figure, like here, this is a specific type of sinusoidal wave. We are not interested in this that how it is drawn and why I draw in this specific shape. Actually this is given. We are just wanted to discuss that this is a waveform, and if this waveform is provided to us and in question the examiner asks us to calculate the voltage or charge, then what we will do? Actually we need to understand the parameters. First of all, the examiner definitely provide us the basic parameters that are definitely current. The value of the current will be given. Then we can easily use these parameters to find out or calculate our current. So we need to find the voltage that provides this waveform of current and associated charge, but as a function of the time, assuming that the L remains constant. And so here the first thing is the inductance is constant to make this case pretty much easier. So again, recapping our formula that we developed, that is the reason we developed the formula. Actually in today's episode we are recapping the formulas. So V is equals to L di over dt here. This is taken from the episode number 5 of equation 5 of episode 12. This is the reference given in the sidebar. Voltage can be found by differentiation of the current and the multiplying with the inductance L. So this is a very simple formula that basically tells us about how we can calculate the voltage. If we have a fixed inductance, you can just derivate the current that is varying with respect to time. You can see this is a sinusoidal, it is continuously varying. So what we're gonna need to do here, if we have a particular value of the time and a current, you're gonna use this and easily just differentiate according to the mathematics rules and find out the voltage. And if this graph looks like that, this is just the graph that are visually exposed, and for the conceptual purpose they are not taken and derived or drawn for the specific values. So this doesn't means that this graph is actually for this doesn't means that this graph is actually for this waveform. This is actually a general graph, and with the passage of the time this is a sinusoidal behavior shows as well for the voltage, and voltage can be found by differentiating the current and multiplying with the inductance according to the formula. So now the third case is the charge. So we already derived a formula in terms of the charge also, because in terms of the current, because in today's episode we have a current. If we have a voltage, let's suppose, then we have also the formulas that are in terms of the voltage for finding charge and the current. If we have one term, then other will be calculated. That is the main reason we already derived too many formulas. Right now we are able to calculate the charge and the current, charge and the voltage if we have a current, like in today's case. So charge can be found by integration of this current to give, so this is actually GIVEN given, uh, charge can be found by integration of the current to a given to give oh sorry it's so fine to give the result. This result, actually this is a graph that is calculated if we have a current, and like here if we have this type of current and there is a fixed values, then what we're gonna need to do is apply the integral limits, usually negative infinity to time t. This is prior to the switching time period, all the time period, and this is the present time. We can divide this time period into two half portions. First portion, you know, is easy to start, easier to find out, and all the time period to the switching is provided to us, so keep this also in mind. This is actually taken from the episode 8 equation number 2 as a reference. Here we have a system that consists of three different coils that are mutually linked to each other. This is coil 1, 2, 3. We named them according to their system. This is the system or circuit number 1, circuit 2 and circuit 3. The current flowing through them is also named after the circuits I1, I2 and I3. We must be able to apply all those concepts that we discussed in the previous section and revise them by applying these concepts to this system that the coils that produces the flux linkage and magnetically coupled with each other. So let's apply them into this discussion. To simplify our discussion, we are just going to suppose that just for understanding for the first portion of this episode, I'm just going to suppose that the current right now have a fixed value, and I2 and I3 are 0, only I1. If I2 and I3 is 0, these systems are almost dead. They are based on another system. If there is a flux produced in the system 1 due to current I1, this flux definitely has a range, and if other systems are bring into this range, they will be able to catch some magnetic field lines that in our system or in our language we will call it as a flux linkage. So the flux linkage in the system 2 and 3 will produce a current I2 and I3 respectively, but it depends upon the mainly I1, because this is I2 if will be induced in the system 2 due to the flux linkage of I1, and same is the case in the I3 depend upon the flux linkage of I1. So this is a primary source, and other are the inductive or the passive source where we can connect our system, our load, and easily use them, like in the case of the transformer primary and the secondary coils. To simplify our discussion, the above three coils are considered as 1, 2 and 3 systems and their currents as I1, I2 and I3. Right now I2 and I3 is 0, so only the effect is due to the I1. The current I1 produces flux linkage psi1s. So if the psi1 is produced due to the I1 in the circuit I1, in circuit 1, then we simply can calculate the flux linkage as L1 and I1. So this is a very simple formula that is used for calculation of the flux linkage in any system. L is used because this is the flux linkage that is produced in this any system is due to the flux of its own current. So the main reason I'm using L here, like here in this coil, if the current the flux is produced because of its own current, so we are going to consider it as a L, means the flux that is self-induced. If we have another case like the flux that is produced in the coil number 2 due to current I1, we will consider it as a M, means mutual inductance, because the two systems are now involved. Whenever there are more than one systems, we are going to consider a mutual. Mutual means the collaboration of more than one in a task, means in the induction or the production of the flux in a system due to another system results in the mutual inductance. Like in here, if the flux is introduced in the coil 1 due to current 1, we will call it as a L1. So the flux linkage is equals to Li. The subscripts 1 1 1 represents that the I1, L1 flux and the flux linkage 1 of the circuit 1. L1 is here for the self inductance in other system, and other circuits I1 will produce same number of the flux link, some number of the actually due to I1 there is a flux produced. We call it as a psi1, and due to this psi1 this I1 actually produced some flux linkage here and here, so we call them as a mutual inductance because the involvement of the two coils. In our system, psi2 is equals to means for the coil 2 it is the formula will be mi m2i 21 and i1. What here I am doing again, as I already discussed that when in the previous episodes, there is whenever we discuss the mutual inductance, the subscripts are two in number. Actually, because mutual inductance is based on the two circuits, like the first circuit, that is the reason to produced, that is the responsible for the production of the effect, while the second thing that need to be highlighted in and need to be shown in the mutual inductance is the circuit where the current or the any flux is introduced, like 2 actually here represents the flux in the coil 2. The second here subscript represents due to current 1. Understood? Means again, flux linkage of system 2 is equals to mutual inductance in system 2 due to current 1 and I1. Flux linkage in system 3 is equals to M3 1 means flux linkage in system 3 due to current 1 I1. In general cases, there are more than one systems. If we have a system, there may be either one is taken as a source, other may be considered as a load. Sources and loads are the two main categories that we will use and in our systems. The first one, which is behaving as a source, the second one, which is behaving as a load, depends upon our configuration, upon the current, and in the previous page we already discussed that the current 2 and current 3 is 0. But now if there is a current in the, like this is a coil 1, and suppose there is another 3 basically coils, and the current 1 here 1, this is current 2, this is current 3, none of them is 0, all currents there have specific value. The flux linkage right now we are going to discuss is the additive, means all the flux that is introduced in 3 cases is in such a way that they are coupled, their direction of the coupling, their winding direction is same, they are additive, the direction of the current is such a way they are additive. So there are the negative also. We are not interested in them right now, we will discuss them in chapter number 2. Okay, this is system 1, this is system 2, and the third one is this. We need to define right now for the system 1, like in the previous case when there is a current 2 and current 3 is 0. The flux linkage of system 1 is very simple. What was that? At that time flux linkage is simply due to its own flux, that is L1 means the inductive system, so and I1. But right now there are the other currents too. Means that if there is a current in the I2, maybe it produces a flux that also has a very wide range, and that affect this portion too. So this comes in the jurisdiction of the system 2. Then we need to consider the other flux at that time too, either they are additive or the negative. But right now I said that all the effects are in the additive system, so we need to consider the effect of the network 2 and the effect of network 3 also when we are discussing the flux linkage. So plus, due to this system, due to the flux linkage due to system, this is now taken as a mutual inductance. I am speaking very important discussion right now. Please note and understand it. Forget about the writing. You can write and note all the things again by repeating the episode, but just consider this. If you click this point, definitely you will be able to understand all the episode very easily. This is a very important point. Whenever we are going to discuss the flux linkage in the coil 1, this is the current that is flowing, which is I1, and the L1, due to inside it is L1, the self inductance first and then mutual inductance. Mutual inductance with this is taken as M. Mutual inductance in coil 1, mutual inductance in coil 1 due to circuit or current 2. This is the current 2. Actually we are taking the case of this circuit, first circuit. First, the flux in total flux in this circuit 1 is first its own flux, and then the flux of the coil 2, the inductiveness of the second coil, that is taken as mutual, because this is not its own, it is the cooperation mutual of the second and first. We are going to take this as a mutual inductance, and mutual inductance of the coil 1, mutual inductance in coil 1 due to current 2, and then multiplied with the current, which current? I2, and then going to add it. Now we are taking the consideration of the flux here, considering the third one. If there are the more systems, we will consider the fourth system also. Again, if we are considering the third system, again this is a mutual, because this is a cooperation of the one or more coils. Only the self will be considered, self inductance will be said when the flux is produced in the same coil. Then we will say that this is self inductance. Mutual inductance for the due to this system in the circuit 1 will be mutual inductance in coil 1 due to current I3 is taken as I13 and now I3. So this is very important. Same is the case, we will derive the equation for side 2 for flux linkage in the system 2, but in now we are going to discuss something with another color. For flux linkage of this system, we are going to define another rule here. Now first we are going to understand the effect of this in system 2. The network 1 here is taken as a mutual inductance right now. Why? Because this mutual inductance means that the coil 1 is producing its effect into system number 2. We are considering now system 2, this system. Now the effect that is produced due to I2 is taken as a self inductance, while and when we are discussing the flux linkage in the network 1, this network 1, then we said that the self inductance due to I1. while the self-inductance now will be due to I2 because we are considering the system number 2. So while the I1 is now, it's for it, this system is taken as a mutual inductance. Mutual inductance in coil number 2 due to current 1 and multiplied with the current 1. Okay, this is now for the mutual inductance with the circuit 1, plus now we have the self inductance of the coil number 2 due to current 2. It's on is taken as self. Again mutual inductance, when we going to develop a relation with the third one, we are considering as a mutual inductance. And now this time for the coil number 2 due to current 3 and multiplying with the current 3. Now the final case is here for the discussion of the mutual inductance of the coil number 3. And now again mutual inductance in coil number 3 due to current 1 first and then I1 plus mutual inductance for the coil number 3 due to current 2 and then multiplied with current 2. Now this is the self inductance for when we are going to discuss the case number 3, network 3. Its own current what produces the flux, that is taken as the self inductance. Self inductance L3 and I3. So this is the three equations that are the base of the further discussion. The total flux of the coil 1 will be the flux linkage produced by the current in the coil number 1 plus the flux linkage produced by current I2 and I3 also, because they are not 0. So if they are 0, again the previous equation is verified that we discussed in the previous page will be verified. If you put the I2 here 0, this whole term will be 0, this whole term will be 0 because I3 is 0, then psi1 is equals to L1 I1. So this is true if we have the current I2 and I3 are 0. But if we have the current I2 and I3 non-zero, and this is the most practical case that they are not 0, then we will use these equations. So number this as equation number 1. This is the same equation that I write here on the other smooth draw. That's the same equation. Psi1 is equals to L1 I1 self inductance, then the mutual inductance due to current 2, mutual inductance due to current 3. For the coil 2, mutual inductance due to coil 1 and self inductance, and the mutual inductance due to coil 3. Then for the coil number 3, we will consider the flux linkage as a mutual inductance due to coil 1, mutual inductance due to coil 2, and then finally the self inductance. Coefficient of the mutual inductance are in the symmetric manner. You will here see very beautiful and symmetric manner of the coefficients of the mutual inductance, not self, mutual. Here we have two subscripts. Its coefficients are like rows and columns. Remember, very beautiful, and a history of the matrix are recapped in your mind when we discuss rows and columns of mathematics. Here the matrix is when we have different elements. First one, there are the two subscripts that representing first row and column. First row, these are the row horizontal, row, second row, third row, while this is first column vertically and this is the second column and this is the third column. So rows and columns are here are represented. First representing the row 1 1 mean the first row first column, first row second column, first row third column, second row first column, second row second column, second row third column. Same is the case you will if notice here. First row second column, first row third column. So this is actually the first row. This is the second row first column, second row second column, second row third column. So this is the third row first column, third row second column, third row third column. If there are furthermore third row fourth column, third row fifth column, and so on. So there is a huge symmetry here. We can also represent them, write them in the matrix format also. So the coefficient of the mutual inductance are the symmetric manner, rows and columns in the subscript. The first is representing the rows while the second is representing here the columns. We are interested in the flux linkage only because it is linked with the voltage, while if it is not linked with the voltage, we are interested in calculation of the voltage from the flux linkage. We wanted to calculate the voltage. So according to the Faraday law from the equation number 4 of episode 11, We know that the Faraday law EMF induced in a coil or any system, inductive system, will be is equal to K d phi over dt. Here the phi is our flux linkage, so going to replace it with the flux linkage. V is equals to d flux linkage. So for the first flux linkage for the system of the network 1, the flux linkage of the network 1 will be derivation of the flux linkage 1 will be the voltage of that network. If we are going to derivate the flux linkage of system or network 1, the result will be the voltage of that network. Now we are going to take the derivation of this flux linkage of this first system, writing the value of the flux linkage 1 from the previous page, L1 I1, M12 I2 and M13 I3. So here if we are going to suppose the inductance is constant, and if inductance is constant, the derivation will be of the variable term, means the current, derivation of the I2, derivation of the I3. So this is the way we can derive the values, and this is equation number 4. This, if we have the values of the current here and inductance, we can calculate the voltage of the system, but we are just really taking this, considering this. So this is again, if we derivate the equation number 2 of the previous system, means the equation flux linkage of the network 2, we are able to calculate the voltage of the system 2. And the same is the case for the system 3. We will be able to use this. Here you can see that the inductance is usually constant, so again inductance is taken as outside the jurisdiction of the derivations. So all the conditions that we discussed in the today's episode are the inductive systems, and the later on in the chapter number 2 and the 3 we will discuss the more complicated cases and the more practical cases. So then we will also consider the negative effects and the negative cases too. So this is the finally end of the episode number 13. We will continue the discussion further next time inshallah, and in the episode 14 we will discuss the next process. Just for your 1 minute I will take more for just giving you an introduction. That suppose that this is the, there are the different types of the system, like here 2, 3 types of total system. First one we were having a capacitive system. Capacitive. We discussed the 3 basic things about the capacitive system, and first one the physical, and then we developed about the field interpretation and the circuit interpretation. Same then we follow for the inductive case. This is the further lecture planning that I'm going to discuss. Again 3 case. The first one case here is again the, what was the first case? Physical phenomena, and then field interpretation, and then the circuit interpretation. Then we are going to move to the final system that is also very important, is the resistive. Resistive system. Again we will try to use the same strategy, that is the physical phenomena, and then field interpretation, and then the circuit interpretation. So this is the further lecture planning. This is what we discussed already. This is discussed. Now it is completed. We already discussed an example case also in today's, and now we are going to switch toward this one. So this is the finally lecture planning, and take care. Allah Hafiz.